Good to have you here for First Principles Daily, episode 36. It's July 11th, 2026. Today, one example of First Principles thinking in action. Cement that binds our buildings costs many times the limestone and fuel alone, because the century-old kiln process itself is the real expense. A cubic meter of structural concrete sells for roughly $100 to $150 in most markets. Yet the rock, sand, and limestone inside it can be valued at commodity prices well below $20. The difference is not scarcity of materials, but the repeated high-temperature baking required to turn limestone into the reactive powder called Portland cement. That gap between raw inputs and finished binder is the opening for First Principles redesign. Cement plants still follow the same basic flow that Joseph Apston patented in 1824. Large rotary kilns standardized the process by the early 20th century. Limestone and clay are quarried, crushed, blended to a precise chemical ratio, and fed into a kiln that reaches 1,450 degrees Celsius. Inside the kiln, the limestone decomposes, releasing carbon dioxide. The resulting calcium oxide combines with silica and alumina to form clinker nodules. The clinker is then cooled and ground with a small percentage of gypsum to produce the final cement powder. Each of those steps is capital intensive and energy intensive because the chemistry demands both heat and the right mineral phases. Once the cement leaves the plant, it travels to thousands of batch plants. There it is mixed on site or nearby with aggregates whose proportions are adjusted for each pour. Specifications written by structural engineers and enforced by building codes require documented performance under decades of load and weather. Any change in chemistry or processing must therefore clear long validation cycles. Financing for a new kiln line runs into the hundreds of millions of dollars. That scale favors large, long-lived facilities that amortize slowly. Fragmented ownership of quarries, trucking fleets, and ready-mix operations adds coordination costs that compound when schedules slip. The result is that the delivered price of cement feels normal inside the industry. The underlying physics of calcination and grinding have not been revisited at the same intensity applied to semiconductors or solar cells. Quarries must maintain consistent chemistry across varying geological seams. This requires selective mining and blending stockpiles that add handling steps before the kiln ever starts. Kiln operation itself runs continuously because thermal cycling damages the refractory lining. Plants therefore carry inventory buffers that tie up working capital. Downstream, ready-mix trucks must discharge within strict time windows to avoid setting. This limits how far a plant can serve and creates regional price variation tied to traffic and permit restrictions on plant siting. Codes treat cement content as a proxy for strength and durability. Contractors rarely optimize below prescriptive minima, even when lab data suggest room to reduce binder. Each layer of this chain reinforces the next. Capital intensity discourages frequent redesign, while conservative specifications reduce the market pull for lower clinker alternatives. A rough magic wand estimate begins with the composition of ordinary Portland cement. About 80% calcium oxide comes from limestone, plus smaller fractions of silica, alumina, and iron oxide supplied by clay or shale. 1 metric ton of cement requires roughly 1.2 to 1.3 metric tons of dry limestone, because the calcination reaction drives off carbon dioxide. Commodity limestone delivered to a plant gate trades in the range of $8 to $15 per ton in most regions. The stone alone therefore sits near $10 to $20 per ton of finished cement. The energy input is dominated by the kiln, which needs on the order of 3 to 4 gigajoules per ton of clinker. At typical industrial fuel prices, that adds another $20 to $40. Grinding and handling add a few dollars more. Adding these commodity values together produces a raw material floor on the order of $40 to $70 per ton, before any profit, labor, or capital recovery. Published average selling prices for bulk cement in recent years have hovered between $100 and $160 per ton in major markets. This implies an idiot index somewhere between 2 and 4. That ratio is modest compared with aerospace parts, yet it still signals that the dominant costs sit in the thermal and chemical processing steps rather than in scarce atoms. The largest single contributor to the gap is the energy required to reach and maintain kiln temperature, plus the inherent CO2 released from the carbonate itself. A second slice comes from the capital charge on the kiln line and the associated permitting and environmental controls. A third slice arises downstream in the conservative safety factors and testing regimes that treat every new mix design as a potential structural risk. Because each of these layers is accepted as standard practice, the finished price appears stable even though the physics of the reaction sets a lower bound that is not dictated by material scarcity. Consider the kiln energy term more closely. 3 gigajoules per ton equals roughly 830 kilowatt hours. Even at 5 cents per kilowatt hour equivalent, the fuel cost alone exceeds the limestone cost. The processed CO2 adds another unavoidable mass loss of roughly 0.5 tons of CO2 per ton of clinker that cannot be recovered without changing the chemistry or capturing the gas. Capital recovery spreads across decades because a single kiln line may produce 2 million tons per year. The upfront outlay still contributes tens of dollars per ton once depreciation, maintenance, and compliance monitoring are included. On the demand side, structural codes often specify minimum cement contents of 300 to 400 kilograms per cubic meter for ordinary concrete. Strength requirements could sometimes be met with 20% less binder if mixed designs were performance certified rather than prescriptive. Each of these increments multiplies. A $10 fuel saving that also cuts emissions still faces the same permitting timeline and the same downstream testing burden. The apparent idiot index therefore remains anchored well above the chemical floor. A redesign would first target the calcination step itself by shifting to chemistries that require lower peak temperatures or that avoid carbonate decomposition altogether. Calcium sulfoaluminate cements, for example, can form at 200 to 300 degrees lower than Portland clinker and incorporate more abundant sulfate sources. This cuts both fuel demand and processed CO2. Realizing that saving at scale would require new raw material supply chains and updated performance standards that certify long-term durability in aggressive environments. A second lever is the partial substitution of clinker with supplementary materials such as ground granulated blast furnace slag or calcined clay. These can replace 30 to 50% of the Portland component while maintaining strength. The limit here is the regional availability of those materials and the need for additional grinding capacity. A third move would electrify or hybridize the kiln using renewable power and pair it with carbon capture on the exhaust stream. This directly addresses the fuel and process emissions. That path depends on the cost trajectory of high-temperature electric heating elements and on durable capture solvents or membranes that can handle the dusty, high-volume flue gas. Downstream, structural engineers could reduce total cement demand by adopting performance-based specifications that reward higher strength mixes or optimized member shapes rather than prescriptive minimum cement contents. Each of these changes collides with the same practical constraints. These include decades-long service life requirements, regional differences in aggregate quality, and the sheer volume of roughly 4 billion tons of cement produced annually. The prize is a material whose delivered cost moves measurably closer to the chemical and thermal floor while cutting the embedded emissions that currently make cement responsible for roughly 8% of global CO2. For the lower temperature chemistry route, the first concrete requirement is a multi-year exposure program showing that sulfate resistance and alkali silica reactivity remain within code limits across climates. Without that dataset, adoption stays confined to non-structural uses. Supplementary materials face a similar gate. Slag supply is tied to steel production, which may decline, so calcined clay must be developed at regional scale with consistent fineness and reactivity. Electrification of the kiln demands not only cheap renewable electricity, but also heating elements that survive continuous 1,400-degree service without frequent replacement. This is a materials problem that has not yet been solved at the required duty cycle. Carbon capture adds its own energy penalty of roughly 30 to 40% of the kiln's heat input in some designs. The net emissions reduction must therefore be weighed against the added capital and operating cost. On the structural side, moving from prescriptive to performance specifications requires insurers and code bodies to accept probabilistic durability models rather than fixed recipes. This shift has begun in a few jurisdictions but remains limited by liability concerns. None of these barriers is fundamental physics. Each is a combination of validation cost, supply chain coordination, and institutional inertia that must be cleared before the idiot index can compress. When the binding agent in the most used structural material on Earth is still produced by a thermal process whose energy penalty and chemical release have changed little in 100 years. The cost structure itself becomes the variable worth redesigning. Standards and validation regimes that once protected public safety can become the next constraint to be solved rather than accepted. Tomorrow, the show returns with another concrete case or another domain where the raw material floor sits well below current prices. The first visible signal that someone is attempting this with cement will be a published durability dataset for a non-Portland binder that meets existing structural codes at pilot scale. That's First Principles Daily for today. If this changed how you see what things cost, share it with someone who'd appreciate it, and subscribe wherever you listen. I'm Patrick in Vancouver. One example or one opportunity every day. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. And before you go, this show is part of the Nerra Network, a family of daily podcasts on tech, science, and markets. Each one a short, sharp briefing you can finish on the commute. If today earned its place in your feed, here's your next listen. Fascinating Frontiers, the most fascinating news from space and science. Find every show free at nerranetwork.com. The age of AI puts real builders on the phone with an AI host. Apply at nerranetwork.com/age-of-AI apply. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own. I'm about to prove